Alright, let x1, x2 all the way into xn be independent and follow a normal distribution with a mean of mu and a variance of sigma squared. Prove that x mean also follow a normal distribution with a mean of mu and a variance of sigma squared over n. So let's use the MGF method because that's my favorite method. And let's use one of the properties of MGF, which I'll call property 1, which states that if the moment generating functions of two random variables are the same, it means that those two random variables follow the same distributions. Alright, once we've established that, it's suffice to say, to prove that if the moment generating functions of x mean equal the moment generating function of a random variable following a normal distribution with a mean of mu and a variance of sigma squared over n, then x mean would also follow this particular normal distribution. Therefore, we just have to find the moment generating function of x mean and the moment generating function of this normal distribution and see if they are equal. If they are, then we proved whatever we wanted to prove. Now let's look at the right-hand side first, because that's kind of easier to find. So let me remind you of a moment generating function of a normally distributed random variable. So just like a very normally distributed random variable is e to the mu s plus sigma squared over 2 s squared times s squared. So since in here the variance is sigma squared over n instead of sigma squared, you just replace sigma squared over n with sigma. You just replace like the sigma squared over here with sigma squared over n. So that would be e to the power of mu s plus sigma squared over n times 2 times s squared. Alright. So that was pretty easy, right? But now we're trying to find the moment generating function of x mean, which is not quite so easy. But we can use a property to help us. Let's call it property 2. Property 2 states that if x1, x2, all the way into xn are independent, then their moment generating function of them added up together is equal to the moment generating function of their individual components multiplied together. You could find this property on Wikipedia and everything, or I can probably prove it in one of the future videos. And since we already know this property and we know that x mean equals to x1 plus x2 plus blah blah all the way into xn over n, which means it's also equal to, okay, so this is just the definition from the prompt, and which equals to x1 over n plus x2 over n plus blah blah over xn over n. This is like a simple addition rule. Then the moment generating function of x mean, which is what we want to find, equals the moment generating function of x1 over n plus x2 over n plus all the way into xn over n. This is just the definition of x mean, and which equals from this property that it equals to the moment generating function of x1 over n multiplied by the moment generating function of x2 over n all the way until moment generating function of xn over n. This is because we already know from the prompt that x1 to xn are independent, and thus x1 over n, x2 over n, etc. must also be independent because n is just a constant. And now we know this, we also know that these values are basically the same because x1, x2, etc. follow the same distribution, which means x1 over n, etc. also follow the same distribution. And from property 1, we know that if two things follow the same distribution, this also goes backwards too, then their moment generating functions are the same. So we know that these values are the same, so we can kind of simplify this into the moment generating function of any x over n to the power of n, because these values are the same, multiplied n times. Now, our goal is just to find the moment generating function of x over n, so that we can use this thing that we found to find the moment generating function of x mean. So to find this, it's kind of difficult as well, because we know that x follow a normal distribution, and normal distributions are usually pretty difficult. So we kind of want to use the standard normal distribution to help us. So basically, we kind of want to find the moment generating function of z over n, where z equals x minus mu over sigma, and follow a standard normal distribution, because that's way easier to find than the moment generating function of a normal distribution over n. Alright. And we know that since z equals x minus mu over sigma, then z over n, we just basically divide both sides by n, must equal to x minus mu over sigma n. And okay, I'll leave this little function like this for now, and then I'll tell you how to find the moment generating function of x over n later on using this formula. But first, let's just try to find the moment generating function of z over n. I know you might have a lot of questions of why we are doing that. It's just because it's a easier technique to solve, and you can get x over n from z over n, which I'll tell you later. So from the definition of moment generating function, the moment generating function of z over n is the expectation of e to the power of sz over n. So that would equal to the integral taken from negative infinity to infinity of e to the power of sz over n times the PDF of z. Alright, so the PDF of a standard normal distribution is 1 over root 2 pi times e to the negative z squared over 2. This is the definition of a standard normal distribution, which can be found in a textbook. And then we combine the two Euler's numbers. You just add the exponents up together. And this is still really hard to solve, right? It makes kind of no sense. So to make a bit more sense, I'll take this out and try to turn it in a format that would make this integral easier to solve. So I'll copy the exponent out. Okay, so the first thing I want to do is take the negative out. Oh, okay. I always make this mistake of taking the negative out but not actually taking it out. Don't make the same mistake. Okay, and then the second part of what I want to do is also take the 2 out, because why not? If you don't know what I'm doing here, I'm basically trying to mimic the PDF. Okay, so what we're trying to mimic, something that looks like this. A PDF of a standard, no, not a standard, of a normal distribution. Because if we find something of the format of this format, then that taking that integral would just be 1, right? Because this is the PDF of a normal distribution. Okay, so a normal distribution. Okay. So I'm trying to make this part look kind of like that part. So I'm taking the 2 out. 2s z over n plus z squared. Okay. Now to mimic the top part, so we already have a form that kind of looks like this part. We have the negative, we have the 2. But then to mimic the squared, we kind of have to complete the square. So now let's complete the square. If you forgot, let me remind you. So actually in this case, since we have negative, the square of a minus b equals a squared minus 2ab plus b squared. Alright. So now we know that we can set, for instance, b as z. So b squared would be z squared. And this part kind of looks like this part, right? So we can set negative 2ab as negative 2sz over n. And then in here, b is just z. We kind of establish that. And then we can kind of cancel out the negative, the 2, and the z. So that will leave us with a equals s over n. So, and then we know that if a equals s over n, a squared will equal to s squared over n squared. Alright, now we have this information. We want to complete the square. So that would equal to A. Like we want to make this format, a format where it's like a perfect square. So we know that A is S over N. So A squared is S squared over N squared. But if we add A S squared over N squared, we have to minus the thing by S squared over N squared. And then we just copy the rest down because we know that 2AB, negative 2AB is negative 2SZ over N. And then we know that B squared is Z squared. Alright. And now to completely complete the square, we have to take this part out of the way. Alright. So that would be square root of N squared minus 2 SZ over N plus Z squared. And then we take this out. We take this part out, so we have to multiply it by negative 1/2. So it's basically plus S squared over 2N squared, because the negative cancels out. And then we can complete the square because we already know that this part is a perfect square. So that would be S over N minus B, which is Z minus Z, and then squared plus S squared over 2N squared. Okay, we're making improvement. Kind of. Yeah, we're kind of making improvements over here. So let's just put this back into here and see what improvements we've made. Let's put this back into the exponents to see if we actually mimicked this formula. Right? Okay. Alright, so we have, I'm just copying this part down, negative half S over N. Okay, the arrow is kind of disturbing, sorry. S over N minus Z squared plus S squared over 2N squared. dz. Alright, and then we can take, since this part is not dependent of Z, we can just take this part out. S squared over 2N squared. And then we want to keep the remaining parts to mimic the PDF of a normal distribution. Over 2. Okay. Okay. I guess it's kind of similar, but the Z over here is negative, so let's take another negative out. Let's take this negative out. Negative 1 squared is just positive, so we can cancel this and then put this over here. Alright, so as you can see over here, it's basically this. Let's use another color. So this part basically is the PDF of a normal distribution where the variance is 1 because there's nothing here, nothing here. So the variance is 1, and the mean is over here, S over N. And as I've said earlier, if you take the integral from negative infinity to infinity of a PDF of any distribution, then that's just 1. So now we've established that a moment generating function of z over n is just e to the power of s squared over 2 n squared. Yay, that was not easy. That took a whole quarter of a page or whatever. But anyhow, we found it. Now, that's not our end goal, right? Okay, our middle goal was to find a moment generating function of x over n. So to find that, we've already established that from earlier that z over n equals x minus mu over sigma n. Now, I want to introduce you to property 3 of the AMGF. It states that if y equals ax plus b, then the moment generating function of y equals the e to the power of sb multiplied by the moment generating function of x of SA. Alright. Now, so since we know that z over n equals x minus mu over sigma n, we want to find what x over n equals to. So we multiply both sides by sigma. So z over n times sigma equals to x over n minus mu over n. So x over n equals to z over n sigma plus mu over n. So in this case, sigma is kind of like the a, because the x is kind of like the z over n in here. The sigma is kind of like the a, and the mu over n is kind of like the b. So we want so this equation becomes the moment generating function of x over n is basically the moment generating function of z over n times sigma plus mu over n, which is the moment generating function, which is the e to the s times b, in this case is mu over n, times the moment generating function of z over n times s of s times a, in this case is sigma. Oh, my sigma looks kind of weird. Okay. Alright, so now we have this thing. We just plug everything in. We know that the moment generating function of z over n is e to the power of s squared over 2n squared. But we want to plug in s with s sigma. So s squared sigma squared over 2n squared. Alright. And now we can go back to our end goal. Our end goal was to find m the moment generating function of x mean, which is this. I can copy it down. So we go back to our end goal of finding the moment generating function of x mean, which equals to this. So we plug whatever we found here and inside here. Which equals to e to the power s of s mu times e to the power of s squared sigma squared over 2n. So basically what I did was just cancel out the n here. Now we can kind of add them up together. All right. Now we have the moment generating function of x mean. Let's go back. We've established that if the moment generating function of x mean equals the moment generating function of a random variable following a normal distribution of with mean of mu and a variance of sigma squared over n, then x mean will follow this distribution. And we found that the moment generating function of a random variable following this distribution is e to the power of mu s plus sigma squared over 2n times s squared. And guess what? These are the same. So this is the same as this. These are equal. Oh, let's just say this thing is the same as this. These are equal. Yay. Okay, since these two things are exactly equal, so m, the moment generating function of x mean, is exactly equal to that of this distribution, then x mean must also follow this distribution. Yay! Now we proved what we wanted to prove.